Okay, let's do 4.1, the introduction to radian measure. So we're going to look at a new kind of angle measure. So we're so familiar with using degrees. Now we're going to be introducing radians. Okay, so what we're going to do here is explore this circle that I have up on the screen. Okay, and just before we get into the circle, we're going to just go over a few definitions and vocabulary. Okay, so the first vocabulary is the arc of a circle. So the arc of a circle is the portion of the circumference of the circle, as you can see the diagram. The circumference is the entire going around all the way around the circle, the distance around the circle, but the arc of a circle, or the arc length, is this length of the portion of a circumference of the circle. Okay, and the arc length L, we can denote it as the letter L. We say subtends angle theta. And so if we create lines or radius lines joining from the center of the circle to each endpoint of the arc, then you would say that the arc length subtends the angle theta created by these two radius lines. Okay, so we're gonna just simmer with that definition, or the vocabulary for as we go through the exploration. Okay, so first let's look at this circle. So I'm going to first highlight one of these lines, is this radius of the circle. Okay, now watch as we move this radius. Okay, we kind of twist it around so that it's trying to mimic, that idea of an arc. Okay, so okay, so there we go. So the radius is not quite an arc yet, but if I took the length of this radius and I kind of twisted it so that it perfectly aligns with the circle, then what I've just created is called a radian. Okay, so a radian is just the portion, basically the arc length of a circle that's equivalent to or equal to the radius of the circle, right? So whatever the radius of the circle is, if I can take that and place it on the circumference of my circle, then that is equivalent or equal to 1 radian. Okay, so we're familiar with degrees, right? And going all the way around in circles 360 degrees. Well, this portion of the circle is 1 radian. And we're going to talk about how we can go back and forth between radians and degrees. Okay, so to do that, we kind of have to know how many radians are in a circle. And so I'm going to kind of use this exploration here. Let's see if I can. Okay, so we have 1 radian, right? So we have this radian. Okay, so again, the radius comes out and we line it up with the circumference. There's our 1 radian. Now, if I kind of take this, all right, radian, and so let's start here. So this is 1 radian, like a slice of the pie. If I kind of keep going around the circle, here's 2 radians, okay, and let's just mark something, right there, okay, and then let's keep going. Okay, so here's another radian. Whoops, so we're at like here at 3 radians or so. Okay, so 3 radians so far. And let's keep going around the circle. Okay, there's another radian. All right, and then let's keep going again. Still another one. So here's another radian, and again. Okay, so we have. Whoop. All right, and then there's one, and just a little bit more. Okay, so we've got 1, 2, 3, 4, 5, 6, plus a little bit more. Okay, so that's kind of gives you a sense of how many radians are in a circle. And it doesn't matter what the radius of the circle is; it's always going to end up being the same number of radians going all the way around the circle. Okay, so let's go back to our notes page. Okay, so here we are, the radian measure. The radian measure, theta of a central angle of a circle, is defined as the ratio of the length of the arc, the angle subtends, divided by the radius of the circle. So 1 radian is the angle subtended at the center of a circle by an arc that is equal in length to the radius of the circle. So exactly what I've been showing you in that little demonstration. Okay, so let's compare radians. We were talking about the arc length of a circle. The arc length, if you want to kind of think about what is the arc length of a circle, it's related to like the circumference of the circle, right? If you have c equals 2 pi r, which is the circumference of a circle, and so this part here, 2 pi, is kind of like a radian measure. So what we're gonna, instead of the whole circle, we're just doing an arc, right? So for an arc, we just say the angle theta that we're subtending, angle theta. Okay, so this angle right here times its radius is the arc length. Okay, so we abbreviate arc length with a, and then we just say theta times r. Okay, but in degrees, right, when we work with degrees, we're talking about arc length in terms of degrees. We take whatever the angle subtended by the arc times pi over 180 times the radius. Okay, and that's the arc length when we're talking about using degrees. But we're going to be moving toward using radians more and more and more. Okay, and exclusively radians when we get to calculus. When working with a unit circle, okay, with a radius of 1, so let's say we make it simple. Radius of 1. The length of the arc is basically the radian measure of the angle, right? So if you took this formula, a equals theta times r, you make the radius of the circle 1, then your arc length is just the radian angle theta, okay? So theta, the arc length is the radian. So the radian is a measure of angle theta that, when drawn as a central angle and subtends an arc A, whose length is equal to the length of the radius of the circle. So when the radius is the same as the arc length, okay, so we're saying here arc length is a. If the radius is the same as the arc length, then r over r equals 1, and so we have 1 radian angle. Okay, now what's the relationship between radians and degrees? So you have to think about the entire circumference of the circle, right? So c equals 2 pi r. We can use this arc length formula, arc length equals theta times r. So if we said the arc length was the entire circle, then you would replace that with the circumference of the circle, 2 pi r, right? And so 2 pi r equals theta times r. R's can cancel from both sides. And so this implies that 2 pi is that radian angle, okay? And since we know going all the way around a circle in degrees is 360 degrees, then we can say 2 pi radians is equal to 360 degrees, okay? And then for simplicity, sometimes we divide that by 2 and we just say pi radians is equal to 180 degrees, okay? So we're going to be, this pi, symbol for pi, is heavily used when we talk about radians, okay? Because we're dealing with circles, and pi is really something fundamental to a circle, okay? So just think about that one more time. Circumference of a circle is 2 pi r, right? Going all the way around the circle. And just think of circumference as just a really big arc length going all the way around the circle. So the arc length is theta times r. And so again, we're saying here that theta as a radian for the whole circumference of the circle is equal to 2 pi. Okay, that's what we define as the radian. Now 2 pi, what does that mean, right? 2 pi, 2 times 3.14. Okay, you take a calculator, you're going to get 6 point something, right? 6.28. Okay, so now why is, so 2 pi is just 6.28 when you convert that number. Now, why is that significant? And that's significant because if I go back to this picture here, we counted how many radians is this entire circle. 1, 2, 3, 4, 5, 6.28, right? A little bit of extra there, right? So if we said the one radian is just how much of an arc length is subtended by the radius, right? It's the arc length is equal to the radius. That's 1 radian, 2 radians, 3 radians, 4 radians, 5 radians, 6 radians, and a little bit. Okay, so that's just like saying 2 times pi. Okay, 2 times pi is the number of radians around the circle. Okay, so how do we convert from degrees to radians and radians to degrees? So if we took the idea that 2 pi is equal to 360, or the simpler version pi equals to 180, then all you got to do is take the number of radians you have and multiply it by pi over 180. Okay, just like think of setting up the proportion, right? So here's a proportion. Like if there's theta, if whatever you're converting, theta radians or to degrees, right? So if I have x degrees divided by 180, that's equivalent to theta radians over pi radians, right? So if I was converting from degrees to radians, then I take the x degrees, if I kind of multiply both sides by pi, right? Pi and pi, this cancels with this. So the number of radians is just pi divided by 180 times the number of degrees that you have, okay? And so similarly, radians to degrees, well, if I have theta radians over, and again, the conversion is pi equals 180, so pi equals 180, and then on the top here is x degrees, okay? So if I had radians to degrees, I enter in how many radians. Let's, and then let's multiply both sides by 180, so that these cancel. Okay, so then if I took 180 divided by pi, which is exactly what I have here, 180 divided by pi times the number of radians I want to convert, I'll get the number in degrees. Okay, so these are just two quick conversion factors that will help you convert from degrees to radians and radians to degrees. So multiply by pi over 180 to convert from degrees to radians, and then multiply by 180 over pi to convert that radian number to degrees. Okay. So just a note, the unit measurement radian is not required to use if the answer is in pi format, okay, but for exact measurement, we'll let pi equals 3.14 approximately, then the unit measurement of radians is required to be used, okay? So what this says is sometimes we're going to put our answer in terms of pi, okay? So that's fine. It's understood to be radians, okay? But if you're giving me a decimal answer, then you're going to have to indicate that's radians, okay? Before we get into some examples, let's talk about another quick concept in this chapter, angular velocity versus linear velocity. So we are very much used to linear velocity, right? The change in distance over the change in time, okay? Going in a straight line, measured in meters per second. However, we have applications where we have angular velocity, something rotating, okay? And angular velocity is the rate of change of the position of an angle of an object with respect to time. So think of theta rotating around a circle, something spinning around the Earth, like a satellite going around Earth or the moon going around the Earth. There is angular velocity, okay? Even swinging a string with an attached mass on it, okay, that has angular velocity. So anything with rotation will have angular velocity, and that's defined as the angular displacement, which is how theta changes over the change of time, okay, and that's equal to omega. So that is another thing we're going to explore as well in this lesson. So let's go through some examples. So let's look at example 1. Let's determine the exact radian. So if we're given something like 65 degrees and we have to convert it to radians, we're going to go back up to this formula, convert to from degrees to radians. We're going to multiply by pi over 180. Okay, so 65 times pi over 180. Okay, equals, I'm going to write it like this, 65 over 180 pi, and I'm going to reduce the fraction to lowest terms. I can reduce this to 13 over 36 pi, And that is my radian, right? So since I'm putting pi, it's understood to be radians, but in most other cases, I'll put radian. But if it's understood to be pi, I will read this as a radian angle measure. Okay, 351 degrees is my next one. So again, take 351, multiply it by pi over 180. Okay, so then you take the fraction 351 over 180 times pi, you reduce it to lowest terms, 39 over 20 pi, and there you go. There's your radian angle measure. Okay, now if we're asked to determine like an approximate radian measure for 218 degrees, so the idea is you take 218, multiply it by pi over 180, okay, and then we get, so if we're approximating, then this is where you take pi and you go 3.14 divided by 180, okay, and then when you multiply it, you're going to let pi, let pi be approximately equal to 3.14. We don't have to go any more than 2 decimal places for this kind of question for pi, but my answer will be quite a few here. So 3.8, your calculator will say 3.80288, but we'll just say that is 3.80. And then in this case, when you're not expressing it in exact values, you're not using pi, I'm going to have to say here 3.80 radian. Okay, you don't want to confuse this for being a degree angle, you have to say radian. Okay, if we're going back from radians to degrees, okay, so you may be given this, here's a radian angle measure, 2 pi over 7. What is this in degrees? Then you're going to use the other conversion factor. So you take 2 pi over 7 multiplied by 180 over pi, 180 degrees over pi, okay? And then now the nice thing about this is that if everything's always in terms of pi, then your pi's cancel, and you're going to get 2 times 180 over 7, and we can simply express that as 51.4 degrees. That's 4.3, we're around to 51.4. All right, 5 pi over 9. So again, multiply this by 180 over pi. We can cancel the pi's. 180 times 5 divided by 9 equals 100. Okay, yeah, degrees. So you just include the degree symbol is there. So there's 100 degrees. 5 pi over 9 is 100 degrees. Okay, so here's another question. An arc of a circle measuring 22.5 centimeters subtends the central angle of 4 pi over 3. Okay, so I'm going to just kind of, it's always nice to visualize, right? So here's a, let me draw a better circle. How about using an exact circle here? There's a circle. Okay, so what's 4 pi over 3, right? Pi is, pi approximately something like this. Okay, 4 pi over 3, just a little bit, it's a pi and another third, so maybe a little bit bigger than what I originally drew. So let's say that's 4 pi over 3, approximately, roughly speaking. Okay, roughly, I don't have an exact protractor here. And the arc of the circle measures, subtends that angle. So this arc is 22.5 centimeters. Okay, find the approximate radius of the circle, okay, to nearest tenth of a centimeter. So let's do this work here on the side. I need a little more space. Okay, so we know, let's draw that circle. Oh, here's my circle. Okay, so what do we know? We know from the radius, we have a radius. If we have another radius, the arc A subtends that radius. Okay, and we know theta, we know the radian angle there, so we know we have that little formula. The arc length equals the radius times the angle theta. Okay, and if we know the arc length 22.5 centimeters equals the radius we do not know, but we know theta is 4 pi over 3 radians. Okay, so I can simply solve for r. Okay, and so if I multiply both sides by, well, how do we solve this? Let's get more room here. Okay, So how do I solve this? If I multiply both sides by 3 over 4 pi, 3 over 4 pi, 4 pi cancels with 4 pi on the right side, 3 cancels with 3, and I'm left with r, okay? And so solving for r, we get 3 times 22.5, which is 67.5 divided by 4 pi, that's equal to r. And then if I let pi equals 3.14, then r equals 67.5 over 4 times 3.14, which is roughly 5.374 centimeters, or I can just round that to 5.4 centimeters. Okay, so there is the radius. That's how you would find the radius of a circle. Okay, angular velocity. So let's look at another question here. During a bicycle race, the back wheel of Katie's bicycle rotates 150 times in 1 minute. Again, rotation. We're going to have angular velocity. Determine the exact angular velocity of the wheel. Okay. All right. So sometimes, how do you visualize angular velocity? What does that mean? Okay. So I'm going to try and explain that, especially if, I mean, this is talked about in physics, especially engineering. If you ever go into engineering, you look at angular velocity quite a bit. We're talking about, like, you have a bicycle wheel and you just, pick a point, put a chalk mark on that wheel, that little white chalk mark. And what we're talking about is, what is the velocity at that point, right? So as it goes around the wheel, it has, the velocity is often, we say it's tangential to the wheel. I mean, like tangent line, right? So tangential to the wheel. And then so as that point moves around the circle, its velocity tangent to the wheel, velocity tangent to the wheel. Okay, so it has these velocity, think of the velocity vectors, for example, that point tangentially outwards. But so I'm assuming this wheel is turning counterclockwise like this. All right, so what we're interested in, right? So if we have, okay, this circle has a radius, okay, radius. What we're interested in is, what is that angular, so if we have this W there, what is that angular velocity? Okay, so angular velocity is the angular velocity is the rate of change of angular displacement, right? So omega, here we have angular velocity, right? Theta is our angle measurement, or we can say displacement, okay? And T for time. So when we describe angular velocity, the formula is just the change of theta. That's the displacement. How does the angle change from one position to the next, divided by the change in time? Okay, that's angular velocity, and it's very much parallel. You can draw the parallels to linear velocity, where linear velocity is the change in displacement over the change in time. Okay. So before I get into that problem, we can look at another example of something that bring it home to something real, like Earth, right? So Earth rotates, right? Earth has an angular velocity, right? So can you calculate Earth's angular velocity? So think about what is the length of one rotation of the Earth? And we were familiar with that is 24 hours, right? It rotates every 24 hours. So that's the change in time, okay? And then, well, how long is one cycle of the rotation of the Earth? We talk about the change in the angle, right? And the change of the angle is, well, 360 degrees. Like think of a rotating in a circle, right? It's 360 degrees. So one cycle equals 360 degrees. Okay. So if one rotation of the Earth is 360 degrees divided by a 24-hour period, then we get an angular velocity of 15 degrees per hour. right? That's really what angular velocity is. The Earth rotates 15 degrees every hour. But now when we do angular velocity, we're going to be also be doing it either with 3 degrees or with radians. Okay, so going back to the bicycle example, here we have Katie's bicycle rotating 150 times in 1 minute. Okay, determine the exact angular velocity in degrees per second and radians per second. Okay, so again, if I use that formula for angular velocity, we have the change in theta over the change in time. Okay, so we have 150 times. Okay, so 150 times is not an angle, right? But we know that a circle is 360 degrees. So we're doing 360 degrees 150 times. So we're going to multiply those two numbers. Okay, and then we're going to divide it by the change in time. So 150 times in 1 minute. So okay, that's going to be, if we do it per second, that's going to be 60 seconds. Okay, so I'll try and stick to SI units as much as possible. So 150 times 360 divided by 60 is going to be 900 degrees per second, right? Because the unit on top is degrees, the unit on the bottom is seconds, right? So degrees per second would be my unit for the final answer. Now, what if I was to do this in radians? Okay, radians per second. Let's take some empty space here. So my angular velocity would be 150 times. What is the angle in radians for one rotation? We know that is 2 pi, right? The circumference of a circle. If in radians, the angle going around the circle is 2 pi radians, right? So 150 times 2 pi divided by 60 seconds. So 150 times in 1 minute. Now, the nice thing I like about radians is that I don't have to do any kind of special decimal answer. I can write everything in terms of pi. So 150 times 2 is 300. 300 divided by 60 is just 5, right? Now I can write my answer in terms of 5 pi, in terms of pi. 5 pi, and then my units are radians per second. Okay. All right. 5 pi radians per second. All right, so let's look at example number 6. The person on a Ferris wheel makes 1 complete revolution in 8 minutes. Calculate the approximate angular velocity of the person in radians per second. Okay, so what do we know? We know that, we know we have 8 minutes. We're talking about 8 minutes. If we convert that to seconds, multiply it by 60, okay, we get 406 times 8 is 48, 480 seconds, okay? And we know 1 revolution of my Ferris wheel in terms of radians is 2 pi radians, okay? And if I multiply 2 times pi, I get 6.28 radians. So we'll do that, okay? So the angular velocity will be the change in theta over the change in time. And so we know 1 revolution, 6.28, can occur over the course of 480 seconds, right? Ferris wheels are not that fast. It's going to take some time to do 1 full rotation. So my angular velocity is 0.013, and then radians per second. Okay. And then my last example, question 7. The shaft of a tractor runs at 540 RPM, revolutions per minute. And there's a picture of a little shaft. Okay, so you can imagine that thing spinning, revolutions per minute, 540 RPMs. Determine the exact and approximate angular velocity of the shaft in radians per second. So this is something that's turning fast, okay? So again, what do we know? The rotation is 2 pi, okay? And it's going around 540 times, 540 revolutions in a minute. So the change in time is equal to 1 minute, okay, or 60 seconds. And so my angular velocity is going to be 2 pi times 540. So 1 revolution is 2 pi times 540 times. To do that revolution, or 540 revolutions. So it's that many radians is going to be 2 pi. So 540 times 2 pi is 1080, right? So 1080 pi radians in 1 minute. Okay, divided by 60 seconds. So that's equal to 1080 pi over 60. And simplifying that, 1080 divided by 60 is just 18. So 18 pi radians per second. Okay. So remember, a single pi is 1 radian, right? So, I mean, sorry, let me say that. 2 pi is just the rotation of a circle. So 18 pi means that we're going to do 9 revolutions, right? In 1 second. Okay. And then if I want to convert this to a little more of a decimal, 18 times 3.14, we get 56.52 radians per second. Okay, approximately. So this is the approximate answer, and 18 pi is going to be the exact answer. Okay, and I like the exact answers way more, and you should start as you progress. I'm going to keep embedding this in your daily math work. Get the exact value. Okay, this serves far more use in future applications in mathematics and even beyond this year. Okay. All right, so that's just the lesson on introduction to radian and angular velocity. You can have a look at some of the practice problems for this lesson. And that's it. Okay.